In the last class, we have completed a theory of small oscillation. Actually, we have developed a theory for the small amplitude oscillation about the stable equilibrium point. And we have summarized the theory via the steps to be followed in solving the problem related to small oscillation. First step was to identify the number of degrees of freedom of the coupled system and to assign suitable generalized coordinates which which denotes the departure of the system from the stable equilibrium configuration. Then the next step is to identify the T and V matrices. Third step is to get the values of the eigenfrequencies from secular determinant. Fourth step is to find out the eters, the small amplitudes or amplitudes of oscillation. This is a coupled oscillation. This equation are the coupled equations. Then the step is to form the modal matrix and to get its inverse, and finally we shall get the normal coordinates jive out of eta and A matrix. With this knowledge, today we start application, and in the next few classes we shall consider few simple examples of the theory of small oscillation. Today we consider a system which comprises of two identical springs, two identical masses, mass 1 connected by three identical elastic springs of each of spring constant K, and the combination is kept on a horizontal frictionless table. So the masses, each of the mass is m and the spring constant is K. This is our system. This is a coupled system because the two mass particles are coupled to each other via this spring. If this spring, the middle spring, were not there, then the system would be an uncoupled one comprising of two isolated two isolated point masses connected by springs. But due to the presence of the middle spring, this is a coupled oscillation problem. First thing, the generalized coordinates are denoted as eta 1 and eta 2, where eta 1 gives us the displacement of the mass particle 1 from its stable equilibrium point, and this gives you the displacement of the mass particle 2 from its stable equilibrium point. Now the kinetic energy. First, coming to the kinetic energy, T is half m eta 1 dot square plus half m eta 2 dot square. This kinetic energy can be written as eta dot T operator eta dot. When we write it explicitly, it reads as eta 1 dot, eta 2 dot. This is the row matrix. Then this is the T matrix, and then this is column matrix. So the result is that this T matrix, actually if we multiply this, let me write it explicitly. This is T11, T12, T21, T22. So first, if we multiply this, eta 1 dot, eta 2 dot is there, and if we multiply it, this is T11, T11 eta 1 dot plus T12 eta 2 dot, and for this T21 eta 1 dot plus T22 eta 2 dot. and if we multiply this with this, we have this multiplied by this. So T11 eta 1 dot square plus T12 eta 1 dot eta 2 dot plus this multiplied by this T21 eta 1 dot eta 2 dot, and this multiplied by this T22 eta 2 dot square. If we compare this equation with this equation, we see that this is equal to m, this is equal to m, this is equal to m, this is 0, this is 0. So we identify the T matrix. So the T matrix, basically the summary is T is equal to half m eta 1 dot square eta 2 dot square, giving T matrix is equal to m times 1001. This is the T matrix. Now coming to V matrix. First, let me find out the expression for the potential energy of the system. Now, since the combination is placed on a frictionless horizontal table, gravity has no role to play, and entire potential energy comes from the springs. So the potential energy V, it is the potential energy of the spring, first spring, which is half eta 1 square, that of this spring, this is half k eta 2 square, and then there is a potential and contribution to the potential energy, which is the coupling term k eta 1 minus eta 2 square. So this can be written as half k twice eta 1 square plus twice eta 2 square minus twice eta 1 eta 2, and obviously the this is the expression for V. And the V matrix is k times 2 minus 1 minus 1 2, because this term has been divided into 2. It is minus eta 1 eta 2 minus eta 2 eta 1. So these are the two contributions. It has been split into two parts. So we have we have obtained the potential energy and the V matrix. If you want to study the stability, we need to find out the eigenvectors of the V matrix. So for stability analysis, what we need to know, we are to find out the eigenvalues of V matrix, which are 2k minus lambda minus k 2k minus lambda, this determinant, which gives us 2k minus lambda is equal to plus minus k, or lambda is equal to 2k plus minus k, so it is equal to k and 3k. Since the spring constant k is positive, both the eigenvalues of the V matrix are positive. And now obviously the stability condition is stable point or equilibrium point is 0, 0. The equilibrium point is eta 1 is equal to 0 is equal to eta 2. And at this point we see that the eigenvalues are positive, so this is a stable equilibrium point. Now coming to the eigenvalues of oscillations, eigenfrequencies. Eigenfrequencies are obtained from the solution of characteristic determinant, that is det v minus omega square t is equal to 0. Here we have 2k minus m omega square minus k, and we have 2k minus m omega square is equal to 0, or we have 2k minus m omega square is equal to plus minus k, or omega square is equal to k by m or 3k by m. We call omega 1 square is equal to k by m and omega 2 square is equal to 3k by m. So these are the eigenfrequencies. Next part is eigenfrequencies. Omega 1 square is equal to k by m, omega 2 square is equal to 3k by m. Then our aim is to find out the eigenvectors. The eigenvectors are obtained from this equation which looks very similar to this. 2k minus m omega I square minus k 2k minus m omega I square a1i a2i is equal to 0. This gives us the eigenvectors. So for omega omega is equal to omega 1 is equal to root over k by m, we have 2k and this is minus k, a11 a21 is equal to 0. This is k, this is minus k. This gives us that a11 is equal to a21 is equal to alpha say. Now how to find out alpha? In the case of matrix diagonalization, we generally normalize the eigenvector, but here we shall use the normalization condition which comes from the fact that summation over ij ailtij aik is equal to delta of lk. If we use this L and K is equal to 1, then it reads as, for L is equal to K is equal to 1, we have summation over Aij, Ai1, this is J, Aj1, Tij is equal to 1. Or we have first I and j 11, so t11 a11 square. Then if I and j both are 2, so t2 to 2a to 1 square. Then the cross term, I is equal to 1, j is equal to 2, a11 a21 t12 plus a21 a11 t21 is equal to 0. This is 0, this is 0. So simply this is m, this is m, and this is alpha and alpha. So 2m alpha square is equal to 1, or alpha is equal to 1 upon 2m. So this is equal to, so we get the first eigenvector. So first eigenvector is a1, or get a1, which is a11 a21, which is alpha 1 this is 1 upon root 2m 1. So this is one finding. So the eigenfrequencies have been recorded. So the first eigenvector a1 is equal to 1 by 2m 1. Now for omega is equal to omega 2, we omega 2 is equal to, for omega is equal to omega 2, for omega is equal to omega 2 is equal to 3k by m under root, we have this is 2k minus 3k minus k 2k minus 3k. This much is multiplied by I is equal to 2. So 1 2 a 2 is equal to 0, which gives us a 1 2 is equal to minus a22 is equal to beta, and we can find out beta like this to be 1 upon 2m 1 minus 1. So this is second eigenvector. Before going further, I like to interpret these two eigenvectors. First thing is, if we put a minus sign before this, nothing changes, because this is just a phase factor which cannot be determined from this. So the message is that if the particle 1 moves towards the right from its equilibrium position, then the particle 2 also moves towards the right, or if the particle 1 moves to the left from the equilibrium position, the particle 2 also moves to the left. So this part, this eigenvector means this is the equilibrium position of particle 1 and 2. This is equilibrium position. Either both shifts towards this, or this is one possibility, or the other possibility is that they both move towards the left. So, and for this case, the equilibrium position is this. Particle 1 is over here and particle 2 is over here. Now the possibility is that either the particle 1 moves towards the right, then the particle 2 moves towards the left, or the alternative is that the particle 2 moves to the particle 1 moves to the left, then the particle 2 moves towards the right. So we see that this is in phase oscillation. both the particles moves in the same direction with the same phase, and this is out of phase oscillation. When one particle moves towards the right, other one moves to the left. So this is the significance of the sign of these eigenvectors. Now with this, I now find out the eta matrices, or eta, the displacement vectors, coupled displacement. So it is in phase oscillation, and this is out of phase oscillation. You recall that the eta matrix, eta was defined to be matrix AK times e to the power I omega kt, sum over k, and which when written in component form we write that eta it is equal to sum over k is equal to 1 to n, here k is 1 to 2, this is n is equal to 2, a ki e to the power I omega kt, and there we remarked that ai may have some page, we may have some page, that is we may have, this is phi k, which is taken, which can be written as summation over k a ki ck e to the power I omega kt, so that eta 1 of t is equal to a11 c1 e to the power I omega 1 t plus a21 c2 e to the power I omega 2 t. We know the value of a11 and a12. This is the a11, this is a21, sorry, a21. So this is 1 upon 2 c1 e to the power I omega 1 t, c2 e to the power I omega 2 t. Similarly, eta 2 of t is equal to a 1 2 c1 e to the power I omega 1 t plus a 2 2 c2 e to the power I omega 2 t, because this ck comes from the phase factor, and so that this is equal to 1 upon 2m c1 e to the power I omega 1 t minus c2 e to the power I omega 2 t. These are the amplitudes. So the summary for the amplitude is eta 1 of t is equal to 1 upon 2m c1 e to the power I omega 1 t c2 e to the power I omega 2 t, and eta 2 of t is equal to 1 upon 2m c1 e to the power I omega 1 t minus c2 e to the power I omega 2 t. Now coming to the modal matrix. The modal matrix is the matrix that is obtained from the eigenvalues. The modal matrix is A is basically A1, A2, this matrix, which in this case is A1, 1, A2, 1, A2, 1, A2, 2. So which is this 1 upon 2 1, 1, 1 minus 1. First thing is the determinant of A. This is 1 upon 2 square root whole square multiplied by minus 2 is equal to minus 1 upon m. This is the det A. Now to find out the inverse of A, let me first write the modal matrix. Modal matrix A is 1 upon 2m 1 1 1 minus 1. First thing, we find the cofactor matrix. Cofactor matrix is obtained by, this is minus 1. If we suppress row and column containing 1 1 element, then if we suppress this element, this is 1. If we suppress this element, this is 1. Oh, there will be an extra minus sign, and this element is plus 1. Then we find the transpose 1. 1 upon 2m, the transpose is itself, minus 1, minus 1, minus 1, plus 1. And then A inverse is 1 upon det A, this is transpose, A cofactor transpose. So det A, so let me write it explicitly. This is A inverse of matrix A is 1 upon det A times A transpose, A cofactor transpose. So there is a factor, minus sign will change this accordingly, and the numerical factor is 1 upon 2m multiplied by m, because the 1 by m was in the denominator, and there is a minus sign which makes all these plus. So this is m by 2, 1 1 1 minus 1. This is the inverse of this. So this is the inverse of A. You can check that A inverse is identity matrix of order 2. Now we have to find out the normal coordinates. The normal coordinates were defined by this. Eta was defined as A matrix times xi, or xi was A inverse eta. A inverse eta. So we have A inverse is 1 1 1 minus 1, and this is eta. So xi 1 is xi 1 of t is equal to m by 2 eta 1 plus eta 2. Now you recall the definition of eta 1. So there is m by 2 here, and we have 2m from there. Then this plus this. So this term goes, and this comes with twice with a factor 2. So this is 2c1 e to the power I omega 1t, and there is a 2, so this is simply c1 e to the power I omega 1t. So this is the first normal coordinate. Similarly, eta 2 is m by 2, this is eta 1 minus eta 2, because this is 1 into eta 1 minus 1 into eta 2. So this is this minus this. So the C1 term cancels out and C2 term comes with a factor 2. So this is simply C2 e to the power I omega 2t. So this is the second normal modes of oscillation. Sorry, this is 2. So we have worked out the entire thing regarding this. Only thing is that if we may also find out the normal coordinates when the initial conditions are given, that were worked out in the last class, that is in terms of eta 1 0, eta 2 0 at 0, the initial conditions when were supplied. So this is a complete workout of the example that we have taken into consideration, that is two-point masses connected by 3 horizontal elastic spring. In this case, to keep the discussion simple, we have taken m1, m2 is equal to m, and k1, k2, k3 is equal to k. If the spring constant were different and the masses were also different, the similar type of calculation can be carried out. Only thing is that algebraic manipulation would become horribly tough. That's why, to keep the thing simple, mathematics simple, still we get the essence of the theory, we have taken a simplified version where the masses are same and the springs are identical. So this indeed shows that in the mode 1, when we analyze the system in terms of normal coordinates, this is the mode 1 oscillation and this is mode 2 oscillation. They are not coupled. But here the oscillation were coupled oscillation. Eta 1, the motion of the particle, the actual motion of the particle 1 is a combination of 2 frequencies, and so is for the particle 2. This is the normal mode allows us to look at the system in a very simple way. Since the motion is not coupled, they are decoupled motion, the energy of the system will be the energy of this mode plus energy of this mode. There is no interaction part in the normal mode analysis. That is why the normal mode analysis is very popular in physics. That's all for the today's class. In the next class we shall consider another example having 2 degrees of freedom.